everyone. Today we are looking at the fundamental theorem of algebra, which is a big title for a big theorem. This really ties a lot of the polynomial stuff we've been talking about together. In all reality, I have probably referred to this theorem many times without even really teaching you what it was, but today is the day that you get to learn the actual fundamental theorem of algebra. And I will tell you that if you look in your book, this theorem is stated in one place, and then there's several other what are called corollaries, which are like related theorems. I've sort of grouped those all together in my wording of the theorem here. So what this theorem is all about is it says that if a polynomial has a degree of n, okay, and remember the degree refers to the highest exponent in the polynomial, that polynomial will have exactly that many roots when we take into consideration both multiplicities and complex roots, okay? So if I have a polynomial of degree 4, one way or another I should be able to account for 4 different roots. Now it's entirely possible that I have a double root or that I have imaginary roots, or, you know, there's all different types of things that can happen there. But one way or another, every polynomial of degree n will have n roots. So I mentioned multiplicities, and this might be kind of hard to read on the screen here, but definition of multiplicity, and for sure we have referred to this in class already, but multiplicity is when you have multiple copies of a zero because you have multiple factors that all give the same zero. So those double roots that we've looked at when we see the graph kind of bounce off a place on the graph, that's what a multiplicity is. So you could have a root with multiplicity 2 or multiplicity 5 or whatever it happens to be based on how many copies of that factor you happen to have. So let's take a look at this first example and we'll start putting this fundamental theorem to use here. In example 1, it wants us to solve by factoring, and then so for solving we're trying to find the roots and we need to make sure to identify any multiple roots. So my first goal here is to factor this thing. So let's look at it and look for a GCF first. And it looks to me like all 3 of these have an x cubed in them. So I'm going to take out an x cubed. And then I'll have, let's see, an x squared minus an 8x plus 16. And now I want to look at this parenthesis and see if that can factor any further. So I'm going to say x cubed. And then how do I multiply to positive 16 and add to negative 8? Well, that would be x minus 4 times x minus 4. Or in other words, x minus 4 squared. Whoops, I don't want to write this squared because I already wrote 2 of them. Okay, and if our goal is to solve by factoring, what we have just found is that we broke this into 3 factors, right? This multiplies together 3 times. So we have either x cubed equals 0 or x minus 4 equals 0. And I'm just doing that the one time because both of these are going to give us the same answer, right? So if x cubed equals 0, that would mean that x would have to equal 0. Really what I did there is a cube root of 0, which is just going to be 0. And then if x minus 4 equals 0, then x would equal 4. So those are our solutions here, but let's pay attention to the fact that this came from an x cubed, which really means, and I don't expect you to write this out like this every time, but this really means x times x times x equals 0, right? So either this x equals 0, or this x equals 0, or this x equals 0. That means I have 3 copies of an identical root, all right? I have 3 copies of x equals 0 because of that x cubed. So I would say that this root has a multiplicity of 3. And then this root came from the fact that I have 2 identical factors. So this root has a multiplicity of 2. And so altogether I have 2 roots, but when I consider their multiplicities, I was able to account for 5 different roots. Basically, it's like my roots are x equals 0, or x equals 0, or x equals 0, or x equals 4, or x equals 4. Okay, so I accounted for 5 roots through multiplicities there. Okay, so let's take a look at example 2 here. This one looks kind of crazy. The degree on this one is 32. So when it says how many complex roots does this have including multiplicities, one way or another I should be able to account for 32 roots here. Okay, this will be a load of fun. Okay, so let's find those roots. So I'm going to take the same approach that I did up here. I'm going to factor this thing. So when I look at what these two things have in common, I can take 30 x's out of them. So I could write this as x to the power of 30. And then I will have a 4x squared and a plus 1 here. Okay, and if I'm trying to find roots, really what I'm doing is setting this thing equal to 0. So think about this right here. If I have x to the 30th equals 0, then that gives me one of my roots already. So let me just write this down. X to the 30th equals 0 means that x equals 0 is a root with a multiplicity of 30. I have 30 copies of that root. Okay. Which means I just accounted for 30 of my 32 roots. So this isn't nearly as cumbersome as we thought it would be. The other two roots are going to come from this guy. Okay. And right now in my head, I'm thinking of like 3 different ways we could solve this thing. I think I'm going to try to stick with factoring just to be consistent with what we've been doing. But after I do that, I'll talk about some other ways that we could solve this. So if I want to factor this thing, in my head, I'm looking at this and thinking that looks an awful lot like difference of 2 squares, but not quite because it's not a difference, okay? So I'm going to rewrite this thing as 4x squared minus negative 1, okay? And then I'm going to factor it as a difference of 2 squares, so I'm going to write it as a plus and a minus. Here I'm going to have a 2x and a 2x. And then in this next spot, I want to be thinking about so that 2x came from doing the square root of 4x squared. Now I want to be thinking about what's the square root of negative 1? What two things would I have to multiply together to make a negative 1? Square root of negative 1, if you remember, is I and I. Okay? And so what this tells me now is 2x plus I could equal 0. Or 2x minus I could equal 0. So if I solve this thing, and I know this is sort of a new thing with the imaginary numbers, but we can do this just like we would do any other problem. If I move the I to the other side, I would have 2x equals negative I, and then divide by 2, and I get x equals negative I over 2, or negative 1/2 I. If I look at this one, I move the I to the other side, I get 2x equals positive I, and then divide by 2 on the other side, and we're going to end up with positive I over 2. So here are my roots. I have x equals 0, x equals negative I over 2, and x equals positive I over 2. These are going to be imaginary roots, okay? These are complex roots, and you will notice that they come in pairs. I believe there's a theorem on the next page that's going to talk about that, but your imaginary roots are always going to come in what's called conjugate pairs, where there's like a plus and a minus of essentially the same root here. And so here's 30, 31, 32. There's our 32 roots. If I was looking at this thing on a graph, and we could graph this one and look at it, this graph's going to look kind of crazy with such a high degree, but this is the only root we would actually see on the graph because this is the only one that's a real number root. These ones we would not see on the graph, but we may see something that sort of indicates a root. Okay, I said I wasn't going to graph it, but I've changed my mind. Let's graph this one. So 4x to the power of 32 plus x to the power of 30. Okay. So we can see here, and gosh, maybe we don't see the thing that would show imaginary roots here. Yeah, I guess not. We see this root of 0, and it's a double root coming from the fact that I know this looks flat. It's not exactly flat. It just, with such a high degree, it really flattens out the bottom of that graph. So that's where my real root comes from. And remember, that counts for like 30 of our roots. That's like a multiplicity of 30 there. And then I have 2 imaginary roots, which again don't really correspond with anything on the graph. Okay, so not super helpful there, unfortunately. Okay, let's go back. Oh, I said I was going to talk about some other ways that we could solve this thing. The other thing I could have done here remember in your calculators, I told you last time to set your calculators for imaginary numbers. So under mode, and I should do mine. This is my calculator at home, so I didn't do it here. You want to be set to a plus bi, okay? So you could do quadratic formula with this thing if you wanted. You would just use 0 for b, okay? So you could do quadratic formula and it would spit out these two answers. I don't have quadratic formula programmed on this calculator, so I'm not going to demonstrate that one, but you could do quadratic formula there. The other thing I could see you doing is we kind of took this thing and factored it into two smaller factors, and then we solved each one of those equal to 0. I could have also just started from here and said 4x squared plus 1 equals 0. And then I could have subtracted 1, so 4x squared equals negative 1. Then I could have divided by 4, and I would have had x squared equals negative 1/4. And then I could have solved by taking a square root. Now, when I take that square root, remember, first of all, I'm going to need a plus or a minus. Square root of 1/4 is 1/2. And then because it's negative, it's going to have an I. So if you look at that answer compared to these two answers, we ended up with the same thing. So one way or another, this is what you're trying to solve. You can solve this one directly because there's no middle term. You could solve this with quadratic formula, or you could break it into smaller factors and solve each one of the factors separately. Okay, so just want to make sure that you've got a kind of a big picture of idea of what you're trying to do here. Okay, let's keep moving. I think our next example here, example 3, this one has us doing some graphing. And let's see. It says to graph, so I'm just typing this in for us. We have x cubed plus 3x squared, whoops, not 22, minus 2x plus 1. And there we go. Zoom out so we can see the whole thing. Okay, so the first question is, how many real roots does this thing have? Real roots are the ones you can point to on the graph. Okay, where do we see a root happening? And I see one root right here. And right now I don't really care about what the actual root is. I don't think I have to care. But I have one real root. I'm going to write this down on our notes page, and then I'll switch the camera back in just a minute. But I have one real root, and that's found by looking at the x-intercept. Okay. So then it says, how many non-real roots does this thing have? And so there's a couple of different kind of considerations we have to have here. This is a cubic function, right? It's a degree of 3. So we know that altogether we should be able to account for 3 roots. I see 1, okay? That means there's 2 more, and so that would tell me that I have 2 imaginary roots, okay? So essentially I took the degree of 3 and subtracted off the 1 real root that we already found, okay? So I know there must be 2 imaginary roots here. This is the thing that I wanted to show you, and the last graph didn't really do a good job of showing it, but do you see how this graph, so it's increasing, right? It's growing, it's growing, it's growing, it's growing, and then it changes direction and heads back down, almost like it's going to go hit the x-axis again, but then it turns around again before it actually crosses the x-axis. But normally this type of behavior would lead to a root. It just didn't dip down low enough to actually cross the x-axis. That right there, anytime your graph changes direction like that, that is an indicator that there are imaginary roots. Now again, I can't find the actual imaginary roots on the graph, but this tells me the fact that this thing dipped down and then turned around and went back up, but without crossing over to 0 anywhere, that there are imaginary roots there someplace, okay? So every time there's a change in direction, that indicates a root of some kind. If it doesn't actually cross the x-axis, that's when you know you're dealing with imaginary numbers. And just one more thing while we're looking at this picture. The last question says, what is the maximum number of times this graph could be intersected with a horizontal line? So the horizontal line we usually care about is the x-axis, right? And the x-axis crosses this graph once. But like if I draw a line right here, let's just say at y equals 5, you can see that that line crosses the graph 3 times. Now, there's nothing special about 5. I just picked that because that happened to work. I could draw a line up here too. I mean, I could draw, y equals 7, and that's going to do the same thing. But that's the largest number of times. I can't draw a line anywhere else and have it hit more than 3 times, okay? So the maximum number of times that the graph could be hit by a horizontal line is 3, which corresponds with the degree of the function. If you notice, this is an x cubed function. That's how I'm going to be able to tell how many reals and how many imaginaries I have. Remember that whole direction changing thing I was talking about? If this green line were my x-axis, I'd be seeing 3 roots here. It just happens that this is shifted so it's not actually touching the x-axis, and that's where my imaginary roots are coming from. So we've got a theorem coming up in just a minute that talks about that. Let's go back to that real quick. Okay. So I've got a couple of, first of all, let's make sure we get our answers down here if you didn't do them while we were talking about them. We saw 1 real root, which means there must be 2 imaginary roots, 2 non-real roots, and the maximum number of times we could hit the graph was 3. So here are a couple of related theorems. A polynomial of degree n can cross a horizontal line at most n times. So the largest number, like if you have a degree of 3, you're never going to be able to hit the graph with more than 3 times with a single horizontal line. And that can help you figuring out like what is the maximum degree that this thing can have. Okay? And then complex non-real roots, so I'm talking about like imaginary roots here, always come in conjugate pairs. So imaginary roots or complex roots always travel in partners. That's why you'll notice up here I had 2. Okay, those 2 roots, if I actually went through the trouble of finding them, would be conjugates of one another. So one would be a positive and one would be a negative as far as like the complex roots go. So those complex roots always travel in pairs, which means anytime I ask you this question, how many non-real roots are there, it always has to be an even number. Okay, there always has to be an even number of imaginary roots because they always travel in partners. Okay. So looking down at example 4, we're talking about some random function p of x, and we don't have an equation or anything to work with, but we know it crosses the x-axis 4 times, and it hits the line y equals 5 6 times. So what can be said about the number of real roots? Well, the real roots are the places where it crosses the x-axis. Okay? So we know that there are 4 real roots. The real roots are always the ones that you can point to on the graph. Okay? So the fact that I can hit this thing 6 times with the line y equals 5 tells me that I must be dealing with at least a degree of 6. Okay? And so if it's at least degree 6 and I have 4 real roots, that would tell me that I have 2 complex roots. There must be at least 2 complex roots. Now, they didn't really tell us if maybe there was another place on the graph that you could hit it more times. That'd be a more complicated question, but that's why I'm saying at least 2 complex roots, because if there's somewhere else that I could hit it 8 times, then maybe I have, 2 more complex roots that I don't know about. But based on the information I'm given, this is what I know. So what does that mean about the degree of P? It must have a degree of at least 6. Okay, it's a degree of 6 or larger. And the reason I'm saying larger is it's possible that one of these is a multiple root. Or like I said, it's possible that there's another place on the graph that you could hit it more times. But you couldn't have a degree of less than 6 because you've got at least 6 roots that you're working with here. Okay, almost done. The last example is the one that I feel like really, really ties everything together. So if you need a minute to catch up, if you need a minute to kind of process and digest, feel free to pause the video now. You want to dive into this last example kind of with a clear head and a full understanding of everything we've talked about so far. So I'm giving you this polynomial function, and I'm telling you that 3i is a 0 of the function. Now, we have to verify that. You have to justify to me why I think that's true. For something to be a 0 of a function, if I plug that, and let me back up here a second. If I said verify that 5 is a 0 of this function, you could potentially go to a graph and graph it and say, hey, look, it crosses the x-axis at 5. But if I'm giving you an imaginary root, you're not going to be able to see that on a graph. So the only way to verify it is like algebraically, okay? So what I'm going to do is think about what it means to be a zero. A zero means that when I plug this thing in for x, it should make my function equal to 0. So this is what I'm doing. I'm going to do, and notice my parentheses here. Parentheses are going to be important. I'm plugging in 3i to the fourth minus 3 times 3i to the third minus 3i squared minus 27 times 3i minus 90. Now, if you were just doing this for your own good, I don't care whether you write it out or not, but if you were doing this on a test or a quiz and I asked you to verify, you're verifying for me. So you better show me that this is what you did to verify. It's not enough to just say, yes, I promise that I typed it in and it worked. So I'm doing 3i to the power, to the power of 4 minus 3 times 3i to the power of 3 minus 3i squared minus 27. Now, we could do this all by hand, right? But that wouldn't be any fun. And then minus 90. And that does come out to be 0. Okay? So maybe make a note to yourself that what I did here was I checked in my calculator. Okay. Then it says, just use this information to find all the other zeros of the function. So the first thing I think is it would be helpful to know what's our goal here? How many zeros am I looking for, right? Well, it's a degree of 4. So that means at the end of this problem, I should be able to identify 4 roots. And it told me one of them, right? We just found that one of the zeros is 3i. The very first thing I'm going to do is use that theorem that we just talked about the conjugate pairs. If 3i is a root, then we also know that negative 3i is a root because these two things are conjugates of each other. So right off the bat, I know a second root. If I know 3i is a root, I automatically know negative 3i is a root. And now I need to find my other two, okay? So, and I'm going to do this all algebraically. In some of these cases, a graph might help, but if the other roots aren't real numbers, you're not going to see them on a graph anyway. So, I mean, you're always welcome to use a graph to help or get you started, but I'm going to work through this one entirely algebraically here. Okay, so remember we said that every time we have a root, we also have a factor, right? And that's really what we want is we want to get these two roots out of there and see what's left over so that we can do something to try to solve that. So I know that, and I'm just kind of jotting this off to the side, I know that x minus 3i is a factor, and also x minus negative 3i, so that'd really be x plus 3i, is a factor. And what I need to figure out is like what's left. I need this. So I'm going to do synthetic division. Now, synthetic division with imaginary numbers can get messy, but as long as you're careful about it, it will work. Okay, so I'm going to divide out these two factors using synthetic division. I'm going to start with 3i as my root, and my coefficients are 1, negative 3, negative 1, negative 27, and negative 90. Okay, so 3i times 1 is 3i. This is the part that might mess with you a little bit. When I go to add these together, they don't actually add together. It makes a complex number, like an a plus bi number. So it's going to be negative 3 plus 3i. Okay. When I go to multiply this, and we can use a calculator to help us here, but I'm doing 3i times negative 3, which makes negative 9i, and 3i times 3i, which makes 9i squared, and that would really be negative 9. Okay, so let me just show you real quick here. If I had wanted to, I could have done this. 3i times negative 3 plus 3i, just so you're not having to do all that distributing. And you're going to get that same thing, negative 9 minus 9i. When I add these next two together, this is what I'm adding, right? Because those are like terms. So I end up with negative 10 minus 9i. And then I'm going to do the same thing, 3i times negative 10 minus 9i. I end up with 27 minus 30i. Again, these are my like terms, so I'm adding those together, and actually that's kind of nice that that cancels, right? Negative 27 and 27. So what I'm bringing down now is negative 30i. And then 3i times negative 30i is going to give me negative 90i squared, otherwise known as positive 90, so this comes down as a 0. And that's what we were expecting, right? We were expecting that to be a 0. That's my remainder. Okay. So now look at this. I mean, if we tried to turn this thing back into a polynomial, tried to put our x's back in this would be a mess. But the good news is we have another factor, right? We have another root here to work with. So I'm just going to dive right into a second round of synthetic division. Bring down my 1. Negative 3i times 1 is negative 3i. These ones always work out real nice. These are going to cancel, so I'm left with just a negative 3. Negative 3i times negative 3 gives me positive 9i, which is going to cancel here, right? And you're left with negative 10. And then negative 3i times negative 10 makes positive 30i, which cancels and makes a 0 here, and that's good because that's our remainder. And now we're back in the land of like nice happy whole numbers, right? So when you're working with the i's, the first round always leaves you with a mess, and then the second round clears that right up because of those conjugate pairs there, okay? So this was an x to the 4th originally. We divided it once and then divided it again. So now what I'm looking at is a quadratic, x squared minus 3x minus 10 equals 0. Okay, this is the thing that would go here. Okay, so we know that my other factor is x squared minus 3x minus 10 equals 0. That's the thing that's going to give me my two other roots. If you wanted to, right now, if all you're looking for is the roots, you could go ahead and do quadratic formula here. Okay, and so quadratic formula would give you your other two answers. Like I said, I don't have a calculator here at home that has quadratic formula on it. So maybe for a second, pretend you're taking the SAT and having to solve a question like this. By the way, I've never seen anything like this on SAT, but having to solve something like this might show up. The fastest way to do that, I mean, you could do quadratic formula by hand, which, ugh, but you can factor this thing. And so I'm going to factor this as x and x. Because this is negative, I know I need one positive, one negative. I need to multiply to 10 and add / subtract to negative 3. So I'm going to use a negative 5 and a positive 2. Okay, so that's going to make a negative 10 if I multiply back together, but 2x and negative 5x will give me negative 3x. And then these factors give me my other two roots. So x plus 2 tells me I'm going to have a root at negative 2. X minus 5 tells me I have a root at 5. So I have two real roots, two imaginary roots. Okay. If I were to graph this thing, so let's get rid of these guys. I'm graphing the original function. Okay. This thing I think is going to just look, does it have a weird dip thing at the bottom? It almost just looks like a parabola, I think. Shrink this up some. But make my y go down to... Okay. So I can see I have real roots at negative 2 and positive 5, which is what we just found. My imaginary roots don't show up on the graph, but this kind of funky shape here, and it's not a true direction change, but that kind of point of inflection there where it kind of bends and then turns back around, that can be another indicator of imaginary roots. So we have 2 imaginary roots here, 2 real roots. If I had just asked you this question on a test, if you had graphed this thing to begin with and found the real roots that way and gotten those 2 out of the way, that would have been fine as well. But you are definitely going to need to know how to do that algebraically the way I showed you, because if these other 2 roots had not been real numbers, if they had been imaginary also, you would not have been able to find them on a graph. Or if you had had multiple roots, you would have to verify algebraically that those multiple roots all held. So sometimes the graph can be a shortcut for you, but not always, so you do want to make sure that you know how to do it by hand as well. Okay, I'm going to pull back over to this screen here, make sure that you've got this last example down, because like I said, that's kind of the important one. This is a big lesson. We're pulling a lot of things together here, so we're going to take some time and practice this. Then we're going to pull it all together with a quiz review, and then we'll take a quiz that covers this stuff, and then that's really the end of your algebra journey. If you're heading on to calculus next year, you'll be revisiting this stuff quite a bit. Okay, this is a really big calculus topic here. So if you do have questions or problems with anything, of course, as always, we'll go over it in class. Otherwise, you guys can take off and have a great day.